Okay, in this example, we have the universal set, and inside of that, we have a single subset A. Now, in the subset A, we have a heart, and outside of that set, but still in the universe, we have a star. So what we want to do is find a few different sets now related to this universe. Okay, so part A says to find U. What is the universe here? So all of the elements in the universe are the star and the heart. And that's everything inside of the rectangle. What's in U complement? So what's in U, but also outside of U? Well, that doesn't even really make any sense. The complement of U is just the empty set. So if you have a universe anywhere and they ask you for what's outside of that, it's always just the empty set. What's the empty set complement? Well, then that would be the U or the set of the star and the heart. So here's an interesting one. It says, what's an A complement? And then that is to another complement. So what's an A complement's complement? Okay, well, first let's think of, like I've said in the past, first of all, what's in A complement? So what's not in A? That's the star. So what is then the complement of this? So what is the complement of the set star? So what's not where the star is? That's the heart. That's the set with the heart in it. Or that's just A. So that leads us to the conclusion that a complement negates another complement. So if you take A and then you complement it and then you complement it again, you're back to A again. What is the union of A and A complement? So what is an A or in A complement? Well, what's in A is a heart, and then what is in its complement is a star. So we end up getting the entire universe in this case. And what is in A intersect A complement? So what's in A and also in A complement? Well, nothing. There's nothing that's in A and at the same time not in A. So this would be the empty set, whichever way you want to write that, either the braces with nothing inside of them or the circle slash. So this just leads us to some kind of, it was a very basic example to lead to some of these conclusions, where if you take the complement twice, you just get back where you started. The complement of the universe is the empty set, and the complement of the empty set is the entire universe, and things like that. Okay, so some operations that you can do on two sets. So this says if you have a universal set and A and B are arbitrary subsets of U, then we have a few rules that hold. So one is the commutative law for union, and then the commutative law for intersection. So all that means is that if I say what's in A or in B, that's the same thing as saying what's in B or in A, because again, the sets themselves, the elements don't matter what order you list them in. So either way, if I do an intersection or a union of two sets, they're the same. A and B is the same thing as B and A. You can just reverse how we write those. May seem simple, but some rules or some laws don't necessarily apply to sets. So these two do apply. And then we have two very unique rules that only apply to sets. These are called De Morgan's laws. So what the first one says is if you take the union of A or B, all in parentheses, and you complement that, what happens is that you actually get the same thing as if you were to complement each set independently and then use the other symbol. So the set A or B in parentheses to the complement is the same thing as A complement intersect B complement. So again, the symbol switches on you. See, you might want to write down so that you remember it later, is that the symbol switches. So it's not just like being able to attach the complement to each one. The symbol has to switch for it to work. And the same thing works for A intersect B, that set complemented. That's the same thing as A complement union B complement. So again, if I want to take away the parentheses and I want to put the complement on each set separately, you have to switch the symbol. And you may or may not believe me at this point that that's what happens. So what we're going to do is we're going to look at some Venn diagrams to kind of prove these to ourselves. So the first one we want to do is find A or B, that set, and then find the complement of that. So doing this how we have been doing it, we would first say, what is in A or in B? Well, that would be, in this case, 1, 2, and 3. And then what's in the complement of that? So what's in A or B, that set complemented, that would only be the number 4. So that would be everything outside of these circles would end up shaded. And that probably makes sense. A or B would be anything inside those circles. So the complement of that is anything outside. So let's see, is that actually the same thing we would get if we do it the other way? So what is A complement intersect B complement? Because we're told above that these two are supposed to be the same. So let's see, A complement, everything outside of A is, if it's outside of A, that would be the set of 4 and 3. Okay, now in a different color, I'm going to find B complement. So what is outside of B? Outside of B is the 1 and the 4. So what is then in both of these? What is in A complement and in B complement? That's just the element 4. So that would again be everything on the outside of these circles. So we've just proven that De Morgan's law works. Okay, so let's prove then to ourselves the second De Morgan's law. Let's prove to ourselves that the intersection of A and B, all complemented, is actually the same thing as taking the separate complements and union them. Okay, so on this one, A intersect B, that set, where do they intersect? That's just the element 2. And so then if we take the complement of the set just containing 2, the what's outside of that, that would be the 1, the 3, and the 4. So everything outside of the intersection. Okay, so what's in, we already know in A complement, we already did this, that's 4 and 3. And we know that B complement is the 1 and the 3. Sorry, the 1 and the 4. And that's from our prior work. So what is in A complement union or B complement? So in one or the other of these, that would be the 1, the 3, and the 4. So we get the exact same